right, so summarizing what we've learned thus far about transmission line activity, we know we have a total voltage, which is the sum of the voltage created by the plus and minus propagating wave. We have a total current, which is the sum of the current created by the plus and minus propagating wave. And those two complex functions of position and frequency are related by a line impedance function, which is, of course, then likewise a complex function of position and frequency. Essentially, we define the line impedance function as the ratio of V to I, sort of a Ohm's law for the transmission line, but an Ohm's law that works on a point-by-point basis. In other words, for each and every location on the transmission line Z, there will be a line impedance value, and then that will constrain the ratio of the total voltage to the total current at that one point. All right, this looks an awful lot like circuits, and in fact, if we go through and sort of change our continuous index of position Z to a countable index in for V1 and I1 and Z1, it would look very much like what we'd have for a linear time invariant circuit with analysis of sinusoidal excitation, time harmonic excitation, where everything is complex and the characteristics of the device are comprised by their impedance value there. So we'd be certainly used to seeing this in circuits class, although again the indexes would be discrete as opposed to continuous here. Because of that, students are like, okay, I think I got this now. Let's move on and do something interesting. All right, so that viewpoint, I call the circuits viewpoint, total voltage, total current, and line impedance function, certainly is valid for basically solving any problem along our transmission line. But it turns out there's an alternative way to expressing transmission line activity and finding answers. And again, I emphasize this word alternative. This isn't an addition to, it's an instead of. And it's sort of like going between Cartesian coordinates and polar coordinates. Each one has applications where it makes the solution easier. We wouldn't always want to solve things in Cartesian. We'd likewise not to want to always solve problems in polar. We pick the tool that is appropriate for what we're trying to analyze to simplify our analysis and perhaps give us better insight as to why the analysis works. And so if this were Cartesian, let's go on and see the from a analogy standpoint, let's see the polar coordinate alternative to the circuit viewpoint. So the first step here is to come up with alternative fundamental functions. From a circuit standpoint, we can say our fundamental functions are voltage and current, the total voltage and total current for a transmission line, those complex functions of frequency and position. But if we look at the total voltage and the total current, and even the resulting line impedance function, the ratio of the two, we see that all of these functions can be written explicitly in terms of the plus wave voltage and the minus wave voltage. The complex function of position and frequency, which is the voltage manifested by the plus going electromagnetic wave, and the voltage manifested by the minus going electromagnetic wave. So all of these can be written in terms of these two functions. So let's say we call the fundamental functions along our transmission line not the total voltage and total current, but the plus wave voltage and the minus wave voltage. Let's think of them as being sort of the bedrock description of what's happening on our transmission line. Well, if that's the case, we ask ourselves a question, what is the relationship between V plus and V minus? Well, our line impedance function was essentially defined by simply taking the ratio of the total voltage of our transmission line to the total current of our transmission line. Again, these are functions of position, and so therefore so is the ratio, the result that we get. So with respect to the plus wave voltage and the minus wave voltage, we can do the same thing. We can take the ratio of these two, and what we're going to do is take the minus wave voltage in the numerator and the plus wave voltage in the denominator. And the ratio of V minus to V plus then is a new function that we call the reflection coefficient function. So V minus is a complex function of position and frequency. V plus is a complex function of position z and frequency omega. And so the ratio of the two, this reflection coefficient function, now is likewise going to be a complex function of position z and frequency omega. Given this definition, we can go through and rewrite this expression. The plus wave voltage times the reflection coefficient function is going to give us the minus wave voltage there. And so this relationship is on a point-by-point basis along the transmission line. As we move along the transmission line, we'll find that every point z will correspond to a different value of V plus and a different value of V minus, and therefore a different value of gamma. But for any location on the transmission line Z, the relationship for V plus at that location to gamma at that location to V minus at that location are satisfied by this equation, or correspondingly this equation here. So the reflection coefficient function is what I call this. It's a function of position. It's not a number, unless we evaluate it at a specific position Z. So one great thing about this reflection coefficient function is we can immediately determine its form. We know what V minus is, the function V minus is. It's the complex wave amplitude V0 minus e to the plus j beta z. All right, that's the V minus function. The V plus function is V0 plus, that complex wave amplitude, times e to the minus j beta z. We take the ratio of the two, and notice these do not cancel. We get plus j beta z and e to the minus j beta z. We combine those together carefully, and we see that we get a complex exponential now with plus j2 beta z. All right. Again, so sometimes students end up canceling these out and getting 0, but if we move the denominator up to the numerator, it becomes e to the plus j beta z, and then we multiply the two together, we end up with 2 beta z here. Otherwise, the other part of it is simply the ratio of V0 minus to V0 plus. And of course, these are wave amplitudes. These are independent of position. The only place where in this result where we see the index position index z is in the argument of this complex exponential. Now, let's go through and evaluate this at one specific spot. We're going to evaluate it at z is equal to 0. This is just like we did with the plus wave voltage, of course. If we evaluate at z is equal to 0, we get the complex wave amplitude V0 plus, a number, or V0 minus, a number. So in this case, we're going to evaluate the reflection coefficient function at a specific location, z is equal to 0, and we replace z with 0 and do the math. We get a number, in this case a complex number, which is simply the ratio of V0 minus to V0 plus. All right, this makes sense. If the reflection coefficient is the ratio of V minus to V plus at any and all locations, then the value of the reflection coefficient function at z is equal to 0 is the ratio of the minus wave voltage at z is equal to 0 to the plus wave voltage at z is equal to 0. And of course, the minus wave voltage at z is equal to 0 is V0 minus. Likewise, the plus wave voltage at z is equal to 0 is V0 plus. And so we're going to give this value its own complex value constant name. We're going to call it gamma 0, just like we called V0 minus or V0 plus. Now we have gamma 0, which is, and always remember this, gamma 0 is simply the value of the reflection coefficient function evaluated at z equal to 0. All right, so we take the results of the previous slide here, and we can put them together and have a new representation of our reflection coefficient function, a function of position z. It's simply the constant gamma 0 times e to the plus j 2 beta z. And we notice this and look at it, and we say this is very similar to the kind of form we got for the plus voltage function, that v plus as a function of z was equal to v plus v0 plus a complex number times e to the minus j beta z. And same thing for V minus, the same form. So we find the reflection coefficient function and the minus voltage and the plus voltage functions really all have the same form, a complex constant followed by a complex exponential that involves a value proportional to the index z. All right, let's go through and see if we can figure out what is the magnitude of this function with respect to position z. We take the magnitude of this reflection coefficient function. The magnitude of the product, remember, of two things is the product of the magnitudes. In this case, the happy news is the product. The happy news is the product of the complex exponential is equal to 1, and therefore the magnitude as a function of position is a constant. Likewise, if we were to go through and try to figure out the phase of the reflection coefficient, it's pretty simple. It's simply the argument here. The phase as a function of position is simply proportional to the value of z with a proportionality constant of 2 times beta. So extracting the magnitude and relative phase from this result is very straightforward. And contrast that to the result that we had if we tried to do that for line impedance. If you recall, we didn't try to figure out, I didn't say what is the magnitude of the line impedance function. And the reason is because the magnitude of the line impedance function is whatever the magnitude of the line impedance function is. We just have to do the math and figure it out. The magnitude of our line impedance, we will find in real circuits, can vary on the same transmission line to something that goes toward infinity and something that can drop all the way to 0 or anything in between. The phase, the phase of the line impedance function, again, is sort of a big mess. We can't really write it down any simpler to say it's the phase of that complex function, the line impedance function. And of course, this was true for total voltage and total current. We couldn't say anything about the magnitude of the total voltage or total current, anything other than that it wasn't a constant of position z. Contrast that to V plus and V minus, where we showed that it was a constant with respect to position z. If we know the magnitude at one location, we know the magnitude at all locations when we're talking about V plus and V minus, and therefore it's no surprise that's likewise true for their ratio, the reflection coefficient function, a constant with respect to position, and a phase, which is very simply written a value that is proportional to index z, proportionality constant of 2 beta. And here we see why we might want to use this different viewpoint of transmission line activity. Instead of total voltage and total current and line impedance, complex functions of position which are not simple and not well behaved, certainly in terms of magnitude and phase, instead we equivalently use plus voltage, minus voltage, reflection coefficient. Functions of position z which are relatively simple and well behaved in terms of certainly their magnitude and their phase. And the simplicity of the mathematics, and later on we'll find the physical description of that simplicity, will lead us in many cases to use the reflection or the wave, what I call the wave viewpoint of transmission line activity, where we have plus wave voltage, minus wave voltage, and the reflection coefficient. All right, just one interesting thing mathematically. We can go through, now that we've defined the value of gamma 0, we can go through and rewrite our line impedance function. Our line impedance function is written in terms of the complex wave amplitudes of V0 plus and V0 minus. Now we know that those are related by a value of gamma 0, and we can do a little algebra and show that the line impedance function can be written directly in terms of the reflection coefficient value of gamma 0. And so this is a bit of a hybrid representation that we have here. Instead of the circuit viewpoint where it's all about total voltage, total current, and line impedance, or wave viewpoint where it's plus wave voltage and minus wave voltage and reflection coefficient function, in this case we've sort of merged the two. We have the line impedance function in terms of a value of the reflection coefficient function that occurs. And this mapping that we have is interesting because it shows that really what we can do is do a direct transformation between the line impedance function and the reflection coefficient function. What we'll find is those two functions are duals of each other, and we can go back and forth. If we know one, we can determine the other. It depends on which viewpoint we're trying to access and use in our transmission line analysis. And this idea of going between impedance and reflection coefficient and back again is a very important transformation of microwave engineering. It leads to a device or a tool that we call the Smith chart, and that's what the Smith chart essentially is doing transformations from line impedance to reflection coefficient and back again. And so we won't talk about Smith charts in this class, but it is sort of an iconic tool in microwave engineering, and it takes advantage of this duality between line impedance and reflection coefficient. All right, so just to kind of summarize and go back over what we've done, again, there are two equivalent ways of describing the activity on a transmission line. The first I call the circuits viewpoint, and that involves the fundamental functions of total voltage and total current and their ratio, which is the line impedance function. Once again, line impedance is not characteristic impedance. All right, and this is far different in many ways from the characteristic impedance. Again, line impedance depends on the transmission line and what is attached to it, where characteristic impedance depends only on the transmission line. Characteristic impedance is a real valued number that is independent of position or frequency, where line impedance is a complex value function of both position and frequency. So again, the difference between characteristic impedance and line impedance could not be more stark and more different. So make sure that you understand the difference between those two. So alternatively, and again, I'll say alternatively to the circuits viewpoint, we have the wave viewpoint of transmission line activity. And in the wave viewpoint, we have two fundamental functions, which are complex functions of position and frequency. In this case, the plus wave voltage, the voltage manifested by the wave propagating in the direction of increasing z, and the minus wave voltage, which is the voltage created by an electromagnetic wave propagating in the opposite direction, the direction of decreasing z. These two functions are fairly simple mathematically, and we take the ratio of those two things and we get a function we call the reflection coefficient function. Again, a complex function of position and frequency, and one that is also relatively simple mathematically. So again, whether you use the circuits viewpoint or the wave viewpoint, you can use one or the other. Either one will give the correct answer. Neither viewpoint has any more information or less information than the other. If you can solve a problem with one using the circuit viewpoint, total voltage, total current, and impedance, you can likewise solve the problem using the wave viewpoint with plus wave, minus wave, and reflection coefficient. Again, I emphasize that because sometimes students think that both of these are additive, that you have to use all of these to solve a problem, or sum of part of one and part of the other. But generally speaking, we don't want to do that. It'd be like trying to solve a problem where we have our variables written in Cartesian coordinates and then also variables written in polar coordinates, and we're trying to solve the problem using both Cartesian and polar coordinates simultaneously, or a few coordinates from Cartesian and one from polar. It would be a big mess. Generally speaking, we pick one or we pick the other. Which one do we pick? Well, we pick the one that's most amenable to our solution. What happens oftentimes is students tend to lean toward the circuits viewpoint because that's what they're used to. They're used to total voltage, current, and impedance after all. But hopefully I've shown that the mathematics associated with total voltage, total current, and line impedance is relatively ugly. It's not fun when you're using complex analysis. Again, the magnitudes are all over the map, large, small, everything changes. The phase can't be written in any compact form. So mathematically, it's difficult. If you use the wave viewpoint, viewpoint, the mathematics are much more compact rather, and much simpler to use. The magnitudes tend to be constant with respect to position. The phases change very simply proportional to index z. The other benefit of using the wave viewpoint is it really describes what's going on in the transmission line, and that you have one wave going the other way, one way, and another wave going the other way. That really is a more physical description, and that's why the math really works out nicer, because it is more aligned with the physical reality of that transmission line. So you might say, okay, well, heck, let's just get rid of all the circuit viewpoint then, and let's just use the wave viewpoint. The math is simpler, it's more physically aligned with the reality of the transmission line. Well, the problem that we run into, the place where circuit viewpoint is almost indispensable, is when we start applying boundary conditions. Remember, we said to find the complex wave amplitudes, we got to connect things to either side of the transmission line. At those points, we have to apply a boundary condition statement. And what we find is boundary condition statements are almost always written in terms of the circuit viewpoint. The voltage at this point is something, or the current at this point is something, or the impedance at this location is some value. It becomes much more difficult to write the boundary conditions in terms of the wave viewpoint. And so what we'll find is both viewpoints are very important and useful, and it's helpful to kind of go and flip back from one to the other. And again, that is a common theme throughout microwave and radio engineering, of transmission line engineering, and again leads to a tool that we call the Smith chart.